All right, so we're finally going to break into what is known as the chi-squared test statistic. So this section is titled Testing Goodness of Fit. It also can be referred to as the chi-squared goodness of fit, which is going to denote GOF. So our goal is to kind of determine if we have a hypothesis test for goodness of fit. So sometimes we're going to work with experiments that have more than two possible outcomes. So imagine that a gambler wants to test whether a die is fair. What the gambler's going to do is they're going to roll the die 60 times and count the number of times each of the following numbers come up. So assume we're dealing with a 6 set of die, so 1 through 6. Here are their observations. So we've got 60 total observations to work with. So we're going to have to do what we've been doing with all of our hypothesis tests and come up with a null and alternative hypothesis. So our null hypothesis here should be fairly obvious. It should be that the proportion that every possible value comes up is weighted evenly. So in other words, for each of these different outcomes, we expect a probability or a proportion of 1/6 of the time we get that value. Now our alternative to this is going to be that at least one of these values, of these, I'm going to call them piece of i's, is incorrect. And so this is going to be what our kind of known alternative are in general when we're doing a goodness of fit hypothesis test. So our null hypothesis is going to be a specific proportion that each possible category or outcome is equal to. And our alternative hypothesis is that at least one proportion is wrong. So that's what we're trying to test. We're trying to test if all of these proportions at the same time are things that we're okay with being our expectations, or if we think at least one of these is wrong. So let's talk about how often we should expect to roll each. The expected frequencies that are the mean counts that would occur if the null hypothesis was true. So how are we going to find these? Well, our expectation times the proportion for that category. Again, we can use this sub-I notation because they're all the same in this case. They're all 1/6. So we would take our 60, multiply it by 1/6, and that'll give us 10 for every possible expected value we could have. So assuming the null hypothesis is true, we want to know what we can expect or what we should see between our observed and expected frequencies. So we're going to have kind of two columns here, our observed and our expected. So we have 12, 7, 14, 15, 4, 8 for our observed from above, and for all of these expecteds, we should expect 10 in each of those categories. So if H naught is true, we should expect O and E to be very close. The larger the difference, the more convincing it is that H naught is not true. So then that test statistics that we come up with should measure how big the differences are between O and E. And so this will lead us then to our chi-squared statistic. So this is going to be our test statistic for this goodness of fit. So K is going to be the number of categories that we have. So in this example, it's 6. And we're going to let O sub I be equal to the observed frequencies and E sub I be to those expected frequencies. So that O column and that E column we had come up with. The chi-squared statistic then is going to be the summation from I equals 1 to K of O sub I minus E sub I, capital E, squared over E sub I. And this is how we're going to go ahead and get our chi-squared with K minus 1 degrees of freedom. So I want to point out something here. Normally when we're looking at these degrees of freedom, it's something related to the sample size, but not in this case. In the case of chi-squared, our degrees of freedom is actually related to the number of categories we have, right? So this is something we want to be careful of, is related to the number of categories. So in this case, we have 6 categories. Our degrees of freedom should be 5. Now, we've always talked about how there are assumptions when we're using these test statistics. In the case of chi-squared, the assumption is that all expected frequencies are 5 or more. All right, so let's continue this example we've been looking at. Based on these observed frequencies for the dye, we want to conclude at the alpha equals 0.05 level that the dye is not fair. So again, just to review, our null hypothesis is that our P sub i's are equal to 1/6 for I equals 1 to 6, and our alternative is that at least 1 P sub I is wrong. So then to calculate our chi-squared, what we will do is we will take the observed, and I'll bring the column over here for a second, our observed minus expected, square it, and then divide by the expectation. So the nice thing is we can kind of just remember that the E's are all going to be 10 in this example, and the O's are just going to be the thing that changes. So I can move this a little more off the screen, kind of be right in the corner there. So when we're calculating this, we'll take 12 minus 10 squared over 10 plus 7 minus 10 squared over 10 plus 14 minus 10 squared over 10 plus 15 minus 10 squared over 10 plus 4 minus 10 squared over 10 and plus 8 minus 10 squared over 10. And so when we do all of this, we should get 9.4, and so this will be our chi-squared value that we're looking at. With 6 minus 1, so 5 degrees of freedom. So remember that DOF, just degrees of freedom. Now when we're looking at our p-value, we can kind of do this with two different methods, and we'll talk about both. For the p-value method, what we're going to do is we're going to go ahead and figure out the probability or the area under the curve based on using a certain value for chi-squared and a certain number of degrees of freedom. So here the chi-squared statistic, and I think we've talked about this a little bit before, starts at 0, kind of peaks early, and then keeps going. And these chi-squareds, similar to our student t distribution, these distributions are changed based on the number of degrees of freedom that we have. So here's the mean, which is the degrees of freedom. Here is our value of 9.4. And what we want to do is we want to go ahead and shade this area to the right. So something of note here, chi-squared tests are always right-tailed. Because the bigger the difference is between 0 and the expectation, then the more convincing that the null is not true. So p-value that we calculate is going to come from, we've had normal CDF, we've had CDF, so of course it'll be chi-squared CDF, and here our inputs are going to be our lower bound, our upper bound, and our degrees of freedom. So let's kind of write that down really quick. Lower bound, upper bound, and degrees of freedom. So let's go ahead and find that in our calculator so we can do it together. All right, so looking at the TI 84 Plus Silver Edition, if we go to our distributions, right there under chi-squared CDF, we'll have 9.4, E99 for the infinity, and 5. And when we spit it out, we get approximately 0.0941. Which, if you look at this, this is not less than 0.05, which was our alpha. So this tells us that we fail to reject the null hypothesis. So that was just using the p-value method. We also can go ahead and use the critical value method. So again, the idea with the critical value method is we have our distribution that we're looking at for chi-squared 5, and what we want to know is where is our 9.4 in relation to that value. If it falls, in this case, to the right, then there would be enough evidence to reject. Now we know that we're not going to because the p-value method already told us. So how do we find this chi-squared critical value? Well, in the notes section, so it should be right around where you found the blank version of this note packet, there is a table that has, on the first page, it is finding critical values for the t distribution based on your number of degrees of freedom and your area for one tail versus two tails. And then on the back side of that, or if you're just scrolling on the PDF, the second page, there's one for the chi-squared distribution as well. So what we'll do is we'll find our number of degrees of freedom, 5, and we'll find our area to the right of the critical value, in this case 0.05, and we'll kind of figure out where those meet. And so here they meet at 11.071. So then that means that our chi-squared for value for 5 degrees of freedom and an area to the right of 0.05 is 11.071. And so if we take a look then, there's 9.4, here's 11.071. We are not in the critical region, and so 9.4 is not in the critical region, which means that we fail to reject that null hypothesis. So we don't have a reason yet to believe that this die is not a fair die. Now, I don't know about you, but when we went to calculate this chi-squared value up here, something that I don't think a lot of you probably found fun if you were trying to play along at home. Now, I know I've done this before, which is why I was able to very quickly just kind of say, oh yeah, that's the answer. But it's probably less fun for you guys. So one of the things you can do is, if you have a TA-84 Plus Silver Edition, and other calculators do this too, is there's a way actually to go ahead and get this all calculated for you. So what we're going to do is we're going to go ahead and create 2 lists. So what I did, there's this stat button here. If you go second and then list, in the first list, we want to go ahead and actually we'll go to edit first. So we'll go stat and then edit. We want to use these first 2 lists. And so the first list will be what our O is. This will be our observed values. So let me pull those up again for a second. We should have 12, 7, 14, 15, 4, and 8. And then in our second list, L2, we're going to have each of these expected values. So in this case, they all happen to be 10. And then what you can do is, going back to stat and going to tests, you can go and you can scroll down to this one, or you can go the other way. You want the chi-squared goodness of fit test. The chi-squared test is going to be something a little bit different. We'll get to that in our next video. But the chi-squared goodness of fit test is going to ask you for your observed, your expected, and your degrees of freedom. And then what you'll want to do is, once you've put in your degrees of freedom, which in this case is 5, your observed and expected, you can go ahead and calculate. And it'll tell you what your chi-squared value is, so 9.4, what we had. Kind of just compare it to the things we had. So 9.4. It'll tell you your p-value, so 0.0941. It'll tell you your degrees of freedom, and it'll tell you some other stuff. So that's great. So here, we immediately know what our p-value is, and we can use this to quickly do the p-value test. And if we wanted to use the critical value test, we still are given what our test statistic is, so we can use that as well. All right, so let's do one more example together. But this time we're gonna shake things up a little bit. We're gonna go ahead and make it so that all of these expecteds are not necessarily the same. So a poll conducted by the General Social Survey asked 1,155 people whether they thought that people with high income should pay a greater or smaller percentage of their income in tax than low-income people. So they had these 4 categories, and this is what they observed from their poll. 5 years earlier, it was determined that 18.5% believed the first option, 39.2% believed the second option, 41.2% believed the third option, and 1.1% believed the last option. We want to conclude if the current percentages are different from what we had before. So these are the things we observed. What we're expecting is, since we have 1,155 people and we have percentages, is we have expectations based on those percentages. So we'll have 1,155 times 0.185 for the first category. We'll have 1,155 times 0.392 for the second category to figure out its expectations. 1,155 times 0.412. And then 1,155 times 0.011 for the last thing. So we should get for these expectations 213.675, 452.76. It's a 2. It's very poorly drawn 2, but it's a 2. 475.86 and 12.705. So these are going to be what our values we have to look at are for the expectations. Notice, I think if you add it all the way up, you end up getting pretty close to 1,155. I think there might be a little bit of rounding thing. So this is going to be where we use our goodness of fit tests. And so our null hypothesis is going to be what these proportions are. So P1, the first proportion, is going to be 0.185. Our second proportion is going to be 0.392. Our third proportion is going to be 0.412. And our last proportion we said was 0.011. And our alternative hypothesis is that at least one of these proportions is wrong. So what we'll do is we'll go ahead and calculate our chi-squared test statistic. So that'll be, in this case, all these observed minus expected divided by the expected. So 218 minus 213.675 squared over 213.675 plus 497 minus 452.76 squared over 452.76 plus 425 minus 475.86 squared over 475.86 plus 15 minus 12.705 squared divided by 12.705. Again, probably not the favorite thing to calculate. We should get it roughly around 10.261, which will be our chi-squared test statistic value with 3 degrees of freedom. Why 3 degrees of freedom? Well, we have 4 categories here, and so it's number of categories minus 1, so 3 degrees of freedom. So what we can do is we can use either the p-value or the critical value method. I'm going to go ahead and do both. So for the p-value, remember, you don't necessarily have to do both unless on the test it says, hey, do both. I'm sure that would never happen. Cough, cough, coughy, cough, cough. Know how to do both. So we know is we've got our value of 10.261, and this being a p-value thing and being chi-squared, we want to know the area to the right. And so what we'll do is we'll take the chi-squared CDF of 10.261 to infinity with 3 degrees of freedom. And just to make sure we can put that in our calculator, again, what we want to do is we want to go to our distributions, so second and then above vars is distributions. We'll go down to chi-squared CDF. We'll do 10.261, infinity, 399 for me, and 3. And then we end up with approximately 0.0165, which is indeed less than our 0.05 significance level, which was our alpha. And so since we have it less than our significance level, this tells us we should reject H0. So again, critical value won't tell us anything different, but just for fun, three degrees of freedom, we want to figure out what this chi-squared of 0.05 is. And so again, what we can do is we can go back to this table, and we're on the chi-squared side, 3 degrees of freedom, 0.05, so this third row, 7.815. So this chi-squared of 0.05, 7.815. And so there's that value, 7.815. Here's our value of 10.261. And so what that means is that our test statistic is in the critical region. So 10.261 is in critical region, which tells us that we should reject the null hypothesis. So what that tells us then, again, we want to talk about how we can use this to actually say something. And what we said before was that we had 5 years earlier these opinions, and what we've concluded is that the opinions have changed, or at least at least one of these proportions that we had before is different than what it was. All right, and then again, just to give us one last thing to look at, I want to show you guys how to use the stat menu in order to find all this information as well. So we can go to stat, and we can go to edit, and so we can create our lists. So we can delete everything that we have in both lists. And so we want to go ahead and take these observed and our expected. So our observed is the first column, so 218, 497, 497, not 467, 425, and 15. And then our expected is 213.675, 452.76, 475.86, and 12.705. So we've got our observed, we've got our expected. So now we can quit out of this, go to tests, and we want to go down to chi-squared goodness of fit. Whoop, hit a wrong button somewhere. Chi-squared goodness of fit. Observed is in the first column, expected is in the second column. Now our degrees of freedom is 3, and we want to go ahead and calculate. So again, we get our test statistic of 10.26. We round that to 1. Our p-value is again rounded to 0.0165, so 1.65%. And so what that tells us then is we can use this to say that we have rejected the null hypothesis since our p-value is too small, and because our test statistic is past our critical value. So this is the last two questions on worksheet 9. So if you had gotten kind of as far as you could with last week's video, and you're trying to figure out how to do those last two problems, now that you've seen this, take a look at this. This also will be some of the first things we see on our last homework assignment for the semester. So also start taking a look at that. Although that homework assignment will be better served once you've seen the next video.